Here's a video for week 5 notes. The first week of notes that will be on Unit 2 test on 10/21. On this slide, I'll explain what an ionic bond is, or ionic compound. And that is between something on the left side of the periodic table. And things on the left side, excluding hydrogen, are metals, or cation. And something on the right side of the periodic table, which is going to be a nonmetal, or an anion. And notice how hydrogen is included on that right side of the periodic table. I did include noble gases when I circled them, but generally speaking, they will not form ionic compounds. Also notice the charges that are on this periodic table, where we have alkali metals as a +1, alkaline as a +2, silver +1, zinc +2, and then that aluminum is a +3. I'll explain what a molecular bond is. That'll be between two atoms or elements that are on the right side of that periodic of that line. I guess I'll just circle noble gases for now. And remember, I'm going to include hydrogen. So when two of those bond together, it is a molecular bond, or between two nonmetals. And again, I circled the noble gases, but generally speaking, they will not form molecular bonds, but it might come up. And a metallic bond is something that you could probably hypothesize at this point, where, I don't know, element 24 is chromium. You have pure chrome or pure silver or something. It's just a metal, and that's a metallic bond. Now you can practice these, Alex, for determining if it's ionic or molecular. Like that down there is molecular because everything's on the right side of that staircase, on the right side of the metalloids, and therefore it's molecular. Compared to the top one, you have a metal and chromium, and then carbonate, CO3, is on the right side of the periodic table, at least those elements are. For topic 2 here, you have to know the properties of metals, or of molecular compounds, ionic compounds, and metallic compounds. And you did that in lab. Give a hint of what you need to know. Ionic compounds, so something like NaCl or table salt. If you put that on a stove or try to melt that, that would not melt. So something like ionic solids are going to have high melting points. Or something like carbon dioxide or water, which are molecular compounds, are going to have low. You should have determined that solubility can vary, meaning mixed. Results for these, metallic solids are not soluble. And then ionic solids are either very conductive or weakly conductive, while molecular solids are, generally speaking, weakly conductive. And then as solids, we got no, yes. Now, naming molecular bonds is the easier of the two. Well, it would seem a little bit harder at first, but ionic bonds get difficult. You can look at these examples at the bottom and sort of pick up on, students tend to just pick up on how to name them by just doing them. And these are prefixes you're going to have to remember. So mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. It's usually not too much of an issue for students just to remember those prefixes. And here are two examples of what will be given. These two are better than the previous slide in the fact that shows multiple for that B, for letter B. Note for that A, it's not mononitrogen trifluoride, but it's just nitrogen trifluoride compared to B, dinitrogen tetraoxide. And if there's two vowels in a row, you'll get rid of one vowel, but it's not really a rule for that. We call that naming an oxide. We'll omit the last letter or prefix or ends with A or O. I don't know. I don't really care. But Alex will. This is just sort of the rules, if you like, rules. But it's really not too tough. You have a prefix, name of the first compound. So like I'll just write N3O6. Trinitrogen. So prefix, name of the first element, prefix, hexaoxide, prefix, and name of the second element, ending with IDE. So naming with IDE is somewhat of something to remember, but you know that CO2 is carbon dioxide. So you knew that before took any chemistry class. And it follows that exact set of rules there. You have a prefix, although it's not monocarbon dioxide because there's only one. And then you have the name of the first element, the prefix name of the second element. Here's some Alex practice. These are pretty easy, these are extremely easy. The spelling is probably the only difficult one from at least going in this direction. But I guess what I would want you to see is all these are on the right side of that periodic table, the right side of that staircase, and then hydrogen. And these are more molecular bonds. Now, here is review of, I'm not able to erase what I wrote on the slides, but valence electrons in review. So group 1 alkali metals have 1, 2. So valence electrons are outermost electrons. We'll get into that quite a bit in week 6. But I'm just marking off how many valence electrons are in each of those groups, with helium with 2. They are the outermost electrons, or they're the most important electrons that are important when it comes to bonding. And here are ion charges for those groups. Hydrogen will form a +1 if, I guess in a sense, it doesn't really matter because it doesn't form an ionic bond. So, but in a sense, that whole group there forms a +1 charge. And then we have aluminum over in group 13 forming a +3. And notice how all these metals down here where I'm shading in blue don't really have, other than, again, silver is a +1 and zinc is a +2, but they don't have anything written on them. So what you're going to learn at the end of week 5 notes is that those can have various charges, meaning, say, cobalt, so element 27, can be cobalt 2 plus, cobalt 4 plus, cobalt 3 plus, and there's somewhat of a difficulty or naming them. Knowing that becomes much harder. So Lewis dot structures is somewhat easy, where you have to draw dots based on how many valence electrons they have. And notice how when I draw from 1 dot to 2 dots, I don't draw the dots on the same side. And helium is the most weird one of that, where we have that over there. That comes into play later. But like carbon with 4 valence electrons, all 4 valence electrons are as far apart from each other as possible because electrons repel. So there is somewhat of a reason why you have valence electrons drawn like that. So Lewis structures of an ion. So let's say magnesium has 2 dots around it because it has 2 valence electrons. But if I said, well, what's the charge that magnesium likes to form when it forms an ion? It's an alkaline metal, so it's a +2. Then, because it's a +2, it loses 2 electrons. It's going to lose both those electrons, and therefore that's a Lewis dot structure. It loses both valence electrons. In comparison, let's say oxygen. How many valence electrons does oxygen have? It has 6. 1, 2, 3, 4, 5, 6. What charge does it form? Well, it forms an O2 minus because it's in group 16. That means it gains 2 electrons. And now we're just going to put brackets around it to indicate that it's a charged particle. It has 8 valence electrons now because it goes from 6 plus 2. You gain something negative, you become more negative, and it's going to have 8 valence electrons. Here's an example of all those, a lot of good ones. You know, here they give the initial dot structures, which is real good. For fluorine, potassium, sulfur. So fluorine's in group 17, potassium's in 1, sulfur's in 16. So you know that 17 forms a -1, hence it gains that 1. Group 1 or alkali metals form +1, hence it loses that 1, and there's a plus on that potassium, and then sulfur forms a -2. Now you're going to have to know how and why an ionic bond forms, which is essentially if sodium loses an electron, it becomes positive. So sodium goes to Na plus 1 electron, it becomes positive. And then if that chlorine takes that electron, it becomes Cl minus, becomes negative. Those two then bond together like magnets. And essentially their charges then cancel each other out. Here's something from Alex that you can practice, but I'll just do a couple of these. B5S2 minus, they want to cancel each other out, so you're going to need 2 V's for every 5 sulfurs. That's one where the crossover method works, but what would be better is if we saw that vanadium is a +5, it means that is a +10. On this side, sulfur is a -2, and that makes that a -10. So that crossover method tends to work, but here, like we talked about in class, is zinc 2 plus sulfur 2 minus, they'll cancel each other out. So ZnS, V2S5. So you can't always use that crossover method. Remember what a ionic bond is, and how to name it. Something on the left and something on the right. And like we said, that writing the name, the anion is going to end with IDE. So students usually pick up those after some practice, but it's not like oxygenide or phosphoride, but phosphide and oxide. So here you're going to have to know how to reverse the charge. To do that, you always just look at the anion. So if you get something like this, on the periodic table, you have the anions over on the right side. Notice how all those charges are always something real, meaning you don't have to determine them from uh, anything else. So to determine the cation charge, you have to use the anion charge. So like for that last one, Mn, S2, sulfur is a -2, so manganese must be a 4 plus. And each one of these here are going to have the anion is going to be a known charge. Iodine is a -1, fluoride is a -1, chloride is a -1, so forth. And you can determine the cation charge from that anion charge, and knowing that the charges have to cancel. So here, this is where we have elements that are not +1, +2, meaning alkali, alkaline, or aluminum, which is a +3. Here we have charges that are transition metals or other metals to the left of that staircase that are not aluminum, and they're not in group 1 or group 2. They're also not silver or zinc. Then you have to use a Roman numeral. So these will be good practice. Like the first two, you're going to have to use a Roman numeral, but the second two, you do not. Now here's another example where iron, those charges are changing, so we have to use a Roman numeral. Cesium is in group 1, barium is in group 2, so those do not need Roman numerals. So this is going to be CSI, this is going to be cesium iodide. In barium, we have Ba2 plus. In iodine, we can do the crossover method here, and we have BaI2, and that's going to be barium iodide. And that's because barium is in group 2, cesium is in plus group 1. We know the charge. Otherwise, we have FeI3 because of the crossover method, or FeI2. Otherwise, we have to signify that charge. This is iron 3 iodide. So look at on the periodic table where iron is. It's not in group 1 or group 2. and it's not aluminum, so therefore we have to signify the charge, just like that next one, iron 2 iodide. And here is an example of that. Calcium is in group 2, or the alkaline metals, so we always know it's +2. Magnesium is always a +2 as well, because it's in the same group as calcium. But iron is a transition metal, so therefore has to have a Roman numeral after it. And this is a tough one. Fe2S3. Sulfur is a -2. That makes that a -6 because there's 3 of them. So Fe has to be a +3 because that charge has to cancel out that sulfur. So that's why it ends up being iron 3 sulfide, IDE, sulfur sulfide. So the last topic we'll talk about is polyatomic ions. And we'll hear about polyatomic ions enough to where to some degree they become a second nature. Poly means more than one atom, or poly means more than one, and then an ion means a charged particle. Again, a cation is positive, the anion is negative. So these are the polyatomic ions. That's the sheet, but you'll be given these, and you'll see how we're going to practice them. Once there's 2 cation polyatomic ions, and the rest are anion polyatomic ions. Ions, and I want to memorize. We'll give you these when it's pretty simple. You just match a polyatomic ion with the Now this is where it gets interesting when it comes to naming ionic bonds. Yes, first just write the formulas. Calcium is a 2+, cyanide is a minus. You need 2 cyanides to cancel out the calcium. Since it is a polyatomic and there's more than one atom, we have to put parentheses around it, just like in algebra. Compared to that next one, sodium is +1, bromate is a -1, and they just cancel each other out. So no parentheses are needed. Something students would do here is they'll write parentheses around, but that would be incorrect because you only need parentheses if there is more than one. Same thing with this next one. We have iron and chromate. Those just cancel each other out because they have the same charges. Now, the naming of the compound is going to take some time. Calcium is a group 1 element, or group 2 element. Sodium is a group 1 element. So we don't need Roman numerals, and we don't change the word of polyatomic ion. So we have just what they are. However, so that's going to be iron chromate. I'm going to go on the next slide. we have Fe 2 plus and gosh, I don't know. What was it? Chromate? Yeah, I think so. CrO4 2 minus. So that ended up just being FeCrO4. But iron is not in group 1 or group 2. It's not aluminum. This is iron 2. So since it is a transition metal, we need a Roman numeral for it. So these are some real good examples of difficult ones when it comes to naming these. The first one was Cr2 plus and NO2 minus. If I had to write the formula here, we can do that crossover method, or better yet, we know 2 nitrites, so you'll be given the polyatomic, and so you'll know that NO2 minus is a nitrite. Will be needed to cancel out that Cr. Chromium is then not in a +1 or +2. It's not an alkali or alkaline metal, or it's not aluminum. So then you're going to need a Roman numeral to indicate the charge. So NO2 is nitrite. So this ends up being chromium 2 nitrite. We don't change the wording of polyatomic to "ide" or anything. Like earlier with just 2 elements, without a polyatomic we would change it to "ide," like sodium chloride. Here we keep the name the same. The next one shows that chromium, being where it is in the transition metal area, can change charges. Now we have a Cr3 plus and CO3 2 minus. This is pretty tough in the sense that there's, the more difficult things of each one where these do not cancel each other out, we need parentheses. So this is going to be Cr2, CO3, 3, because 3 carbonates, so CO3 2 minus is a carbonate, will be needed to cancel out 2 chromium. Now, since that chromium, though, is a 3 plus, which was told it was 3 plus, this has to be chromium 3 carbonate. Hence, again, we're using the Roman numeral to distinguish the charge of the cation. The anion is carbonate, CO3 2 minus. Lastly, we have a Fe 2 plus and a chromate. Now these just cancel each other out, so no parentheses is needed. But yet iron is not in group 1, group 2, or aluminum, nor is it silver or zinc. I should use those as well. Therefore, we have to identify the charge as a +2. This is iron 2 chromate. This is a thing that most teachers give their students. To me, I struggle following it, but I think probably a lot of students might benefit from it, but so for me personally, I don't. But here we have the mention of those like silver, aluminum, cadmium we don't really see, but zinc. Maybe I should teach cadmium, that would just make it easier. But like everything that we have done can be followed by these rules. And so maybe I should give this to students and see if it works out for them, because I never really have, other than early in my teaching career. And so If it makes sense to you, definitely use it.